And thanks and welcome everyone to the High Energy Astrophysics Division seminars on Wednesday. I'm very pleased today to introduce you to our speaker, who is Professor Gary Zank. I'll go through quickly a long list of positions and awards, trying to mention only the most important ones. So Gary is currently University of Alabama Board of Trustees Trustee Professor and Aerojet Rocketdyne Chair in Space Science, also eminent scholar and distinguished professor and director of the Center for Space Physics and Aeronautics Research at University of Alabama at Huntsville. And is also chair of the Department of Space Science at the University of Alabama, Huntsville. Among the previous positions, I can recall the Pei-Ling Chan Chair of Physics at the Physics Department, still in Huntsville. Before then, Chancellor Professor of Physics and Astronomy at University of California, Riverside. Before that, Professor at Bartle Research Institute at University of Delaware. Going backward, he was postdoc at Max Planck Institute for Kern Physics or Nuclear Physics at the Max Planck Institute for Aeronautics in Germany in 1987-89, and then at Bartle Research Institute in Delaware. And he got his PhD in 1987 in Natal, South Africa. So among the awards, the ones which I could mention are, besides the fact he's member of the National Academy of Sciences, elected in 2016, fellow of the American Geophysical Union and of the American Physical Society. He was awarded the Oxford Medal by the Asia Oceania Geosciences Society, the Zeldovich Medal in 1996 for the young scientists below 36 years old. In particular, this was for his work in space plasma physics and for his theoretical studies of mass loading shocks formation in interplanetary space and of the interaction of the heliosphere with the local interstellar medium. I should mention, because Parker Solar Probe result will be discussed today, that he was also co-recipient of the NASA Silver Achievement Medal within the Parker Solar Probe team. He was also recipient of Johannes Geiss Fellowship, awarded by the International Space Studies Institute, so-called ISI in Switzerland. And I was just reading something interesting, that one of his papers titled The Equations of Reduced Magnetohydrodynamics, in collaboration with Bill Matthews, was selected by the editorial board of the Journal of Plasma Physics as one of the 12 classic JPP papers. So the talk of today has a title, Turbulence and Heating of Solar Corona. So it's very much related to our general topics of high energy. We'll see how the Parker Solar Probe, or also theoretical modeling developed based on the most recent Parker Solar Probe data, can what they can offer to advance our understanding of the heating of solar corona. So, and with that, thank you very much, Gary, for being with us, and the virtual floor is yours.
Thanks very much, Federico. That was a very kind introduction. The depressing thing is to hear how long ago it was that I was 36 or under. Anyway, so with that, I thought I'd talk about it. To some extent, this is a little bit like taking coals to Newcastle, talking about turbulence and the heating of the solar corona, but I hope you'll bear with me, and that there will be some interesting new things that you may learn and you may ask about. So if you want more detail, there was a recent paper that just came out. It was a review paper, and so to some extent this talk is based on that, and so one can pull that up and find probably better explanations than I can give verbally. So the problem, of course, is that that is the problem, of course, is the heating of the solar corona, a problem that's really been around for a good 50+ years, ever since the start of the space age, and really perhaps before. And so one of the approaches that has been explored in quite considerable detail now in the past, I don't know, perhaps 5 years, is going back perhaps a decade, but particularly in the last 5 years, has been the idea that somehow turbulence is related to the heating of the solar corona. And so I have on the sort of left and right 2 particular cartoons of perhaps the origin of the fast solar wind. On the left, showing some form of coronal hole, where the various surfaces of interest, the sonic surface, the Alfvén surface, are identified. There are the boundaries. There's the possibility that you can have Kelvin-Helmholtz instabilities on those boundaries. I should add that we've just submitted a very interesting paper with Daniel Taloni as the lead author, looking at the possibility that we may in fact have identified in the low corona, using UVCS, the UVCS instrument, and theoretical modeling, the possibility that in fact we've detected Kelvin-Helmholtz-like instabilities low down in the open coronal hole regions. So that is the possible acceleration mechanism, or at least the source of the fast solar wind. On the right is another possible source, but for the slow solar wind, one possibility being that effectively you have heating of a loop via turbulence. And I'll talk more about possibly the same mechanisms for both, but heating of a loop, the loops can undergo some form of reconnection, an interchange reconnection event that releases a blob or a lot of heated plasma, and that sort of gradually moves up and out and possibly forms the slow solar wind once it reaches supersonic and super-Alfvénic speeds. So those in sort of a nutshell are the 2 particular models and the cartoons that many of us have at the back of our minds when discussing either the fast or the slow solar wind. Of course, there are lots of interesting and important details, and some of these will emerge as we go through this presentation. So you can think of the turbulence models possibly in 2 categories, and this was a suggestion that was made by Stephen Cranmer and the late Art van Balagoyen. The one is wave turbulence driven models, sometimes just abbreviated as WT, and the other is this kind of reconnection loop opening, or RLO models. And the first class was one that I was involved with many years ago, in fact, and it grew out of a visit from Ian Axford to the Bartol Research Institute. And Ian at the time he and Jim McKenzie were interested and had introduced this furnace model of how the fast solar wind might be accelerated, how the solar corona may be heated. And he'd given a couple of presentations on this, and Bill Matthews and I were obviously very interested members of the audience, and we were a little critical about the idea. It was then that we sort of realized, largely because we'd been doing a lot of work on turbulence in the solar wind, that this idea that somehow Alfvén waves could only provide a sort of dynamical force to the wind and accelerate it to higher speeds did not necessarily follow if you thought about turbulence a little more. And we had been looking at turbulence transport models and recognized, for a few years prior to that in fact the large-scale gradient of the wind and the magnetic field could result in an effect of reflection. I mean, some work along these lines had been done in the well-known paper by Heinemann and Olbert, but not a great deal had sort of really followed up, and certainly not in a turbulence context. And so we recognized that, in the low corona and a little above, that you would expect that outwardly propagating Alfvén waves would would experience some reflection and then propagate backwards. But the key insight into this is that the counter-propagating Alfvén waves then set up the possibility for a nonlinear cascade through a three-wave interaction, which would induce or generate quasi 2D fluctuations, zero frequency modes. And it is these zero frequency modes that undergo a cascade that then results in the dissipation. And of course, the zero frequency modes are simply advected slowly through the corona. So you don't lose all that energy very quickly. And so you can heat that, so you can heat the background plasma. And so this was the origin of that first paper that Bill Matthews and a couple of us put together in 1999. And so this idea has gained a lot of credence, and in fact has been examined very extensively by including Cranmer and Van Barle-Gooyen and many others. And so that was sort of the first semi-quantitative, I would say, turbulence transport model that was introduced. The difficulty, however, with that still remains this question that most of the energy resides in Alfvénic fluctuations in this perspective, and that the reflection process isn't always very, very efficient. And then there are also complications in how you go through the critical point and what happens to the turbulence there, and whether or not you can get many waves up and out of the chromosphere and then further out into the solar corona. So while a very attractive model, it does have its drawbacks, and so partly as a result of a PhD thesis that was being done by Laxman Adhikari using a particular model where we were examining what might happen in the vicinity of the Alfvén critical point with Alfvén waves, we found great difficulty in propagating Alfvén waves through the Alfvén critical point. And it was then that I sort of started rethinking this idea about whether or not it should be dominated by Alfvénic fluctuations versus structures. By structures, I mean flux ropes, magnetic islands, these small-scale zero-frequency modes that are advected by the background flow. And the idea didn't come out of nowhere, because in fact, in the supersonic solar wind, it is now a reasonably well-established paradigm that in fact most of the energy in turbulent fluctuations resides in quasi 2D turbulence and not in the Alfvénic component. And this allows one to explain, for example, the evolution of turbulence from really almost the Alfvén critical surface all the way out to the heliospheric termination shock. It allows one to explain the heating of the solar wind that's observed in the distant heliosphere beyond about 20 to 30 astronomical units. And also it allows one to explain the behavior of the cosmic ray mean free paths that have always been a challenge based exclusively on models of Alfvénic turbulence. And so the suggestion here was one that I made regarding the turbulence that differed from the Matthews et al. Paper that I'd worked on in 1999, is that if you go down to the magnetic carpet, you have replenishment on something like a 40-hour scale. You generate these sort of mixed polarity loops that are merging and emerging and being subducted and interacting. And in fact, Parker had long ago identified this sort of region as a possible place for nanoflares with the associated dissipation. It's also similar, if you think about it on a very small scale, with ideas that Len Fisk had been discussing about interchange reconnection and heating. So the magnetic carpet seemed to be a very sensible place to go and explore for the origin of zero frequency turbulence. You might imagine that these loops are sort of forming, reforming, subducting, emerging, being moved around, mixed polarity. So what you would be doing is generating a lot of turbulent fluctuations associated with the magnetic field as a result of this process. And so a sort of cartoon illustration is there on the left and on the right, suggesting that in open field regions, you might have this process going on with the magnetic carpet as you would have in closed regions with loops. And so you would possibly generate in the region somewhat above the photosphere with some kind of scale height that corresponds to the extent of the magnetic carpet above the photosphere. You would have a region that generates a lot of quasi two-dimensional turbulence through these slow motion movements and the sort of reconnecting events, the highly dynamical behavior as a source of turbulence. The thing about this, however, which is different from what Parker was suggesting with the nanoflares, is that quasi-2D turbulence is a dynamical cascading of energy through all these different scales and eventual dissipation at small scales, the ion inertial scale or whatever the ion dissipation scales are, and we're still not 100% clear on what that might be. And so what you really need to understand is as the flow advects slowly away from the photosphere, you need to take into account the transport of this kind of quasi-2D turbulence and how it eventually dissipates in the solar corona, whether in open or closed magnetic field regions. And so then one is faced with the problem of dealing with the turbulence transport model in this rather complicated regime. So before I go too much further, I've been talking about quasi-2D turbulence, and I've been talking about slab turbulence, and not everybody's completely familiar with both sets of terms. So let me remind you that slab turbulence is essentially, you can think of it as Alfvén waves propagating backwards and forwards along the magnetic field. It's of course comprised of transverse fluctuations, transverse to the mean magnetic field as illustrated here, but the dependence of these transverse fluctuations is with the direction associated with the mean magnetic field. So in a cartoon form over here, what you might expect then is these vectors would sort of rotate more or less together as they propagate along in either direction the magnetic field. So they have a k-parallel component, and that's kind of illustrated up here on the top. By contrast, 2D turbulence is also transverse turbulence, but now the transverse elements of the vector depend not on the direction of the line, are independent of the magnetic field direction, but are only dependent on the coordinates orthogonal to the mean magnetic field. In other words, x and y in this cartoon here. So within planes orthogonal to the mean magnetic field, you have random fluctuations of these fields. Unlike the slab turbulence, which has propagating Alfvén waves propagating at the Alfvén speed, also circularly polarized and so forth, the 2D fluctuations do not propagate. They're advected structures. They can typically have a kind of helical kind of structure. They look like they are flux ropes projected into a 2D plane. They look like magnetic islands. So people talk about magnetic islands, plasmoids, flux ropes in a kind of interchangeable way. In the supersonic solar wind, where we've studied this for a lot, what we find is that, in fact, in low plasma beta and beta order 1 regimes, the quasi-2D fluctuations are, in fact, the majority, typically at an order or percentage. 80% of the energy resides in the quasi-2D and 20% in the minority slab component. As I said, this is appropriate to low beta or beta order 1 plasma. And I should mention one very nice simulation that was done by Franco Rapazzo and Parker, which looked at a closed loop. And what Rapazzo did was introduce a sort of current 2D turbulence at the foot points of the loop and let that evolve. I believe it was using possibly a reduced MHD kind of calculation. And what he saw there was the development of quasi-2D turbulence and the formation of current sheets. And all that is in fact consistent with a lot of the theoretical work that we had done over the years in developing this kind of description of turbulence and MHD in a low beta and order beta 1 plasma. So you can put together these models, and they're fairly complicated, although I will point out in a minute that there are correspondences that can be drawn between the sort of standard WKB description that most of us are familiar with. But I put this little table in basically showing what the sort of nearly incompressible quasi-2D models would predict versus what the wave turbulence models would predict. And so this is a way of, in fact, exploring whether or not we can manage to distinguish between these two cases and learn what it is that maybe, if it's turbulence, heating a solar corona. So as I mentioned, these quasi-2D models basically say that most of the energy resides in the quasi-2D component with a minority component in slab, both in the energy containing and in the inertial ranges. The cross-helicity, the energy and forward and backward propagating fluctuations, is arbitrary in this particular case. And in fact, you can even have, which is very interesting, the possibility of unidirectional propagating Alfvén fluctuations along the magnetic field, which exhibit a k to the -5/3 or strictly a k parallel to the -5/3 spectrum. Hopefully I'll talk about that. The residual energy in the case of the 2D models can be arbitrary, but it tends to evolve towards a magnetic energy dominated state. And that's an important distinction. And unlike the incompressible models on which the wave turbulence models are built, these nearly incompressible models allow you to look at the evolution of density fluctuations, but the density fluctuations in the leading order are in fact entropic fluctuations. They're not slow mode or fast mode waves, although those enter at a higher order. By contrast, the wave turbulence models have the opposite sort of perspective, and that most of the energy resides in slab, and you bleed some of that out into the quasi-2D state, so that you can then look at the interaction, the nonlinear interaction, and then cascade energy and heat the solar corona. Typically, the turbulence is thought to be isotropic or possibly Goldreich-Sridhar scaling, and this is related to this k to the -11 spectrum that I'll get back to. Because you need counter-propagating waves, that tends to drive the cross-helicity towards 0. So you need something that's close to 0 in order to induce the nonlinear interactions, which means, for one, that k to the -5/3 spectra are not possible for unidirectional waves. Similarly, because it's primarily Alfvénic, the residual energy, which is basically the amount of energy in kinetic and magnetic field fluctuations, has to be small. It's the difference between the two. And so the residual energy, because of the correlation between velocity and magnetic field, would be small for residual energy. And of course, as I mentioned, nothing can be said about density fluctuations in this case. So before we go any further, the question is can we in fact heat the can we in fact heat the solar wind using this kind of nearly incompressible model? And so the sort of calculation that I did in 2018 was very simple. It was essentially a turbulence transport model, assuming a fixed background flow state. So in this particular case, the velocity, density, magnetic field were all prescribed. I just used a linear profile out to just a little beyond 11 solar radii, where we assumed the Alfvén surface was a radial magnetic field, and we solved then the appropriate turbulence transport equations in this particular geometry, and then we tied in the heating to see in a sense test turbulence instead of test particle, test turbulence sense, to determine whether or not the amount of heat deposited in the background plasma would correspond to a sufficient level of heating. And so what you see in this left and right sort of two panels are the energy in forward and backward propagating modes. And in fact, you see that in the backward propagating modes, and this is in the 2D case, so use backward in the Alsace sense, not necessarily in the Alfvén wave propagating sense. What you see is much of the energy is depleted, more so here, but a lot of the forward propagating energy is also depleted. These solid lines correspond to the quasi 2D energy. The dashed lines correspond to the energy in slab fluctuations, and you can see that there's a significant difference between the two. The important point here, even with this extremely simple, rather toy model, is that in fact you can get very rapid temperature increase up to just a little under 2 × 10⁶ K, roughly 2 million degrees, and you can then possibly account for the solar corona. This drop-off treat with some caution because it's a self-consistent model. But you see that the heating can occur very quickly and within a couple of solar radii. Okay, so that's sort of the general background. If you go into Parker Solar Probe data, can you in fact start extracting some of the underlying properties that are necessary to describe turbulence in the way that I've described? So the first thing I'm going to do is take a look and see whether or not you see magnetic flux ropes and alphanic structures from PSP measurements. And this is the sort of work that Lingling Zhao has been doing. There are 2 papers listed here about that. So I don't want to go into great detail. It gets a little bit technical, and unless you're sort of deep in the data analysis of this, it really may just be a little mysterious. So what we did was we developed a technique. Lingling effectively created a way to, or used existing ways and modified them a little bit to calculate the magnetic helicity of the fluctuations. So she could measure the twist in these fluctuations. She also developed a sort of efficient technique to look at the cross helicity and the residual energy. And then we identified search criteria for these magnetic flux ropes. And what we effectively looked at is a set of spectrograms related to the magnetic helicity, the cross helicity, the residual energy. And we also looked at plots like this, which are effectively circular plots. They're sigma c squared, the cross helicity, versus the residual energy, sigma r squared. And if you calculate what that is from the Alsace variables in the forward and backward direction, what you find is that it forms a perfect circle in these quantities. And that if the residual energy is 0 in these regions over here, you would expect that that's alphanic fluctuations. You'd also have to have that the cross helicity, if you have one directional propagating modes, you might find that the cross helicity would be close to 1. So this is a well-known example of outwardly propagating alphanic fluctuations, and you can see that they sort of fall in this area of the circle. Okay, all right. So this is the kind of data we look at. This was from the 3rd inbound traversal of Parker Solar Probe in sort of mid-2019. And what you can see is magnetic field, velocities, density and temperature in red over here, and the plasma beta. And you see the plasma beta tends to be below 1 in all of these cases. And these are the spectrograms for the magnetic helicity, the cross helicity, and the residual energy that I indicated. And so what you do is you use an automated algorithm to go in here and pick out where these particular structures are that we think of as that we classify as flux ropes or magnetic islands. And typically you might find a magnetic island would have some value up where it's nice and red or nice and blue. And you might find then that the cross helicity, that the residual energy would be either red or blue, and your cross helicity may be relatively small. So you might see an example here of high here where I have high magnetic helicity, rather small cross helicity, and high residual energy, meaning that that's most likely a flux rope structure. And you can do this on the 4th crossing. And the 4th crossing here was quite interesting because in this case you had 2 current sheet crossings, which I've just identified in the dashed lines over here. And what we tended to find is that there were a great many flux ropes in the vicinity of the current sheet. Not altogether surprising, because this is going to be a very active region of reconnection, for example. And so you might expect that kind of dynamics to initiate a kind of current sheet kind of flux rope or magnetic island cascade to smaller and smaller scales. And so we then examined all of this statistically, and these are the kinds of plots that I illustrated earlier. This is for the third orbit, this is for the fourth orbit. You can see that you've got lots and lots of alphanic-like fluctuations by this red and blue, outwardly propagating, inwardly propagating in this particular case. And you can see that there's a sort of modest little square here, 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 which correspond to regions where we can definitively say these are magnetic flux ropes. And so you can then examine the statistics of these magnetic flux ropes. You can find, distributions of sizes, you can find where they're common and so forth. And so we go through all that data. You then generate, for example, histograms that show that you have flux ropes present in the third and fourth orbits. You have quite a few. And in this particular case, there's an interesting dependence on the number of events with the plasma beta. It almost has a power law structure, which has been seen in the supersonic solar wind, still not fully understood. There's an interesting little point that you can make here when you look at the plasma beta as a function of heliocentric distance, where you see the flux ropes. And what you find, in fact, is that there appears to be some level of heating. I won't go into this. It's sort of interesting, but not definitive kind of result. Bottom line is that when you examine the coronal plasma that PSP has been passing through, you do indeed see evidence for magnetic flux ropes of multiple scales on virtually all the encounters. These very small magnetic flux ropes are typically 1 to 2 a day in these orbits that we looked at. They seem to be more likely to be observed in the slow solar wind, and the alphanic structures tend to be observed more often in the fast solar wind. And this is an interesting point, because this tends to be a selection effect that's quite often overlooked. Okay, turning now to spectral features in the field-aligned solar wind. You'll recall that in that little table that I'd presented, one of the things that I'd spoken about was this very curious K parallel to the -5/3 spectrum. And so let me talk a little bit about that. So in the solar wind itself, there is this very characteristic property of turbulence, which is that it is anisotropic in various ways, one of which is in the spectrum. And so this became of great interest with the Goldreich and Sridhar papers, where they introduced this idea of critical balance. Critical balance is really just a hypothesis. And they argued that based on the idea that you can have counterpropagating waves and a certain balance between perpendicular and parallel fluctuations, that would lead to a particular scaling of the spectrum in the parallel direction that was distinct from the spectrum that you would see in directions orthogonal to the mean magnetic field. And so orthogonal to the mean magnetic field, you would typically expect to see, according to Goldreich and Sridhar, a K to the perp -5/3 spectrum. Whereas if you were looking in a line, field-aligned flows, you would expect to see a K parallel spectrum that was -2. And so a variety of people, particularly Tim Horbury, went and examined this using Ulysses data. And when they looked at large angles between the magnetic field and the flow direction, they did indeed see something that looked like a -5/3 spectrum. Now, I should add that there is a complication in the analysis that was done by Horbury and many others since then, which is that they used a wavelet analysis, and they looked at the definition of the and so what they did was they looked at a scale-dependent orthogonality or alignment with the magnetic field, whereas the theory, in fact, talks about a well-defined mean magnetic field. And it's not obvious that you're, in fact, picking out a well-defined mean magnetic field when you're doing a wavelet analysis that, in fact, is scale dependent in terms of how it evaluates the mean magnetic field. Nonetheless, they found when you went to quasi-parallel or highly parallel mean field, mean flows, you had this f⁻²⁰ spectrum, suggesting that the Goldreich and Streetar scaling seems sensible. The critical point, however, is that you have to have sigma c close to 0 in order to ensure that you have those nonlinear couplings to generate that f⁻²⁰. So one of the things that Parker Solar Probe should expect to see is more quasi-parallel spectra, just because of the Parker spiral magnetic field and the likelihood of observing more parallel than a field, more radial field than perpendicular field. So Daniel Toloni led a study where what we did was we looked at an enormous amount of wind data, looking for very highly field-aligned flows. And we found a few flows. If I remember correctly, it's something on the order of, I don't know, 17 or 18 that we found in 8 or 9 years of data. So these intervals are very, very rare. And what we did was we used a different technique, and we also used the definition of the mean magnetic field as the theory insists it should be used. And when we did that, what we found in these intervals is they had unidirectional wave propagation. In other words, the sigma c was close to 0, close to 1. And secondly, the power law spectra were typically of the -5/3 form. And so there was an interesting paper that pointed out that intermittency affects the wavelet method quite significantly. This was by Wang et al. In 2014. And so it's entirely possible that these analyses of the spectra in these field-aligned flows could be very easily affected by the method, in fact, that you're using to examine those flows. So Lingling Zhao then went and took a look at Parker Solar Probe data and tried to identify regions where you had very, very clean unidirectional flow. So the flow is highly radial, as can be seen here, and the magnetic field direction, if I look down here, as the theta BN, is very close to 180 degrees. So we found a couple of examples where we had similar field-aligned flows in the Parker Solar Probe data. And lo and behold, what we found is, first of all, if you can see at the top, these exhibited unidirectional wave propagation, so outwardly propagating alphanic fluctuations, very little or almost no inwardly propagating fluctuations. So they were all unidirectional. And with that, we also found that the residual energy was close to 0. So we were looking at alphanic fluctuations. And lo and behold, the spectrum was effectively an f⁻⁵, which, using Taylor's hypothesis, gave us a k⁻⁵ spectrum for these magnetic fluctuations. So this is, again, inconsistent with Goldreich and Streetar. That model relies on the need for counter-propagating waves to induce the nonlinear interactions. And the nonlinearity it transpires that leads to this f⁻⁵ interaction comes as a result of the coupling of unidirectional fluctuations with the background dominant 2D turbulence. And so the nearly incompressible result here for this small plasma beta regime in the solar corona, or at least in the supersonic solar wind just above the heated part of the corona, is that, in fact, it is consistent with nearly incompressible MHD. These are the two intervals, again, showing the spectra, very pretty. I won't go through this, but this is basically a demonstration that in these intervals, the intermittency is very low, so no complications associated with that. So in summary, what we find then is that we have spectra that are consistent with -5/3, and in fact that they're unidirectional propagating highly field aligned flows. So this needs to be folded into our understanding of turbulence. I'm not going to go through this. It gets a little technical in places, but this essentially is the theoretical understanding for why you should expect to see those -5/3 flows for unidirectional waves. This is sort of the analysis. You can show that the Goldreich and Streethouse scaling can kind of come out of this as a special case, but the choice here of this anisotropy results in this 5/3 spectrum as expected. So it appears that the building blocks in part are available to understand then this paradigm for the transport of solar wind turbulence in the low corona as dominated by quasi 2D fluctuations. So what happens then when you take these quasi 2D turbulence transport models and apply them to the actual solar wind modeling itself? And so this is work that Laxman Adhikari has been working on very intensively with applying the models and comparing them in detail to Parker Solar Probe and Helios observations. And so what he's looked at here is just an example, is he'll pick out the dark blue and the light blue sort of regions for PSP encounters, and regard one as high speed and the other as low speed wind, and then try to compare various models against those. So the first thing he did was he looked carefully at the scaling of the density fluctuations, because the theory of nearly incompressible MHD predicts that the fluctuating density in an inhomogeneous flow, such as the solar wind, should scale as order Mach number. And so Laxman looked at that. The fit is over here. You see it's roughly an order Mach number, and you can see also that the values of the delta rho over the mean value of the density are all of about 0.15 or little more than that. And you can also see that the turbulent Mach number is on the order of sort of 0.2 to 0.4, so small turbulent Mach number. So what he's done is he's effectively looked at in this first set of calculations, basically an extension of the simplest of Parker kind of calculation. Basically, the large scale flows are just Parker, just spherically symmetric flows, one-dimensional. He'll introduce the thermal ion pressure, and he'll introduce an electron pressure. But the key to all of this is that there's turbulent heating. So he's dressed this up. He also has proton-electron collisions and things present, but it's this ST, this source of turbulence, the turbulent heating term, that is the important element in introducing these new equations. The ST, the turbulent transport heating term, comes from solving a very rather complicated set of equations. This, for example, is sort of the simplest description. It's expressed in terms of L-Sasser variables and residual energy and correlation functions, which are important because it's the correlation functions themselves that determine the cascade rate and hence the rate at which energy is deposited into the background flow. I won't go through these equations. They're interesting to people who really like equations, I suppose. This is the corresponding transport. One thing I will point out is in the quasi 2D, the only transport sort of background flow effect is associated with the large scale flow velocity. When I go to the alphanic or slab turbulence component, that is modified because now the alphane waves enter, and so you have this composite transport term of u plus minus the alphane speed. And so correlation lengths now refer in particular to the dissipation associated with counter-propagating waves, and you can see that that's kind of the result of this plus minus minus plus. Okay, I don't want to go through that in detail, but I will point out that that very complicated system of equations that I just showed you has a close relationship in some sense, but it is not analogous to the wave energy transport equation that you might derive using WKB theory. And so for those of you familiar with the standard WKB model, you'll see that the left-hand transport term, for example, of the slab turbulence for, say, outward propagating modes, looks exactly like the WKB term. But you've got a much more complicated definition of the wave pressure that involves things like the anisotropy, how the off-diagonal terms are associated with the diagonal terms, or the trace of the Alsace forward and backward tensors. It'll involve things like the residual energy, and so you can do that for the waves. You can do a similar thing for the non-propagating 2D structure, again, where you have a more complicated definition of the wave pressure, if you will, that arises in the WKB description. But it is not analogous. It has the similarities as you would expect because of the natural formalism of the model equations, but in terms of analogy, it is not the same. So what Laxman then does is he looks at a solar wind model, and here's an example of the the fast solar wind. I can't read, but that looks like it's the fast solar wind up here. These are the outputted results. The solid line is the flow velocity from the model. This is dashed lines are the alphane and sound speed. Red refer to velocity observations by Parker, and the inferred alphane and sound speed that you get from Parker, temperatures, solar wind protons, heating rate. So you can see that you do a very good, reasonable job of in fact modeling the flow. Obviously the density falls off, and the observed temperature appears to be consistent, or at least reasonable, with the model. You can then look at the turbulent transport characteristics. So you can look at things like, again, these are sort of bulk parameters using both Parker Solar Probe and Helios data, and trying to go much further out. And you can see that there are several interesting points that I should draw your attention to. Here's the electron temperature, the proton temperature. So this seems to fit quite nicely with a lot of that. The velocities seem to be sort of reasonable. Not sure what goes on there. The entropy appears to be a very useful and interesting measure, as illustrated by the theory and the observations for both electrons and protons. And then, as I said, you can then look at the turbulent fluctuations from the Parker Solar Probe and Helios data sets. And you've got to be careful here, because you're looking, in this case, at field-aligned flows. The comparison has to be, in these cases, with the slab turbulence, not the solid line, which is the quasi 2D fluctuations. And so you can see, in terms of the inward and outward, the forward and backward propagating modes, that we seem to do a very reasonable job, in fact, of matching the observed turbulence transport profile, even not too bad here. And you can see this is the residual energy. So this is the balance, and you can see that it falls pretty nicely. The theory and observations are not too bad. And the cross-helicity is consistent with primarily outward propagating alphanic fluctuations. Most of the energization, however, of the background solar wind flow that accounted for the large-scale solutions matching the background flow are due to the dissipation of quasi-2D turbulence, however. And you can see that in the sort of solid theory curves. And you can also do a very credible job in terms of the correlation lengths, which are, in fact, you kind of would expect, because this is, in fact, what is controlling the rate at which energy is dissipated. Okay. So this is field-aligned flows. This is just looking at the raw data, in a sense, the raw plasma variables, the magnetic field variance in the fluctuations. And you can see it does actually, I would say, a pretty stunningly good job of matching the observations for the slab component. The velocity component, whether in the supersonic solar wind with other spacecraft or here, always looks more ratty, more indeterminate. And so it looks okay, I guess. The density fluctuation, the variance in the fluctuating density is surprisingly good, and that shows a nice result there that is consistent. And this has offered the possibility of trying to use also remote observations of the density variance inferred from pulsar observations and so forth to see how much consistency there is between what we calculate and what seems to be observed by Parker and what is inferred by the people who do those radio measurements. Laxman has also looked at slow wind, and I won't belabor this too much longer. He finds very good correlation with very good correspondence, I should say, with the results that are observed for slow solar wind flows. In this case, you now look at 45, great. In this case, you now look at the quasi 2D and compare that to the Parker observations, and that seems to work pretty well. So in summary, the quasi 2D models seem to do a very credible job of heating the background plasma, both in protons and electrons, although we use an empirical electron physics model that I didn't discuss, but it's one that you may have heard of via Stephen Cranmer. And it appears that the large-scale solar wind and turbulence quantities are consistent with this kind of nearly incompressible dominant M2D minority slab model. Okay, so the conclusions are essentially that we can tick off many of the sort of predictions associated with the quasi 2D model that I described at the beginning. It appears that you do see, in fact, that a majority is quasi 2D and fast and slow wind, and this is consistent. We still don't know enough, although we've got some papers that are submitted about the anisotropy and the inertial range. Again, we see that the quasi 2D has arbitrary cross helicities, but we also see observationally that this curious k to the minus 5/3 spectrum arises for unidirectional wave propagation and field aligned flows, and it's only the NI-MHD model that can provide an explanation for that. Mentioned that the residual energy tends to evolve towards the magnetic energy, and we find that both the k to the minus 5/3 spectrum is observed and also that the variance is quite consistent. So let me close then with just one little result that has just been published in a very nice paper that sort of goes to show the power of using both remote and in situ observations. And this was this particular event on the 2nd of June 20, not the 2022. I don't know why I put that in. This was in, when was this particular? I suddenly forgotten when this was. It was earlier this year, and I'm just forgetting the date, and I put the wrong one in. My apologies. So what effectively happened here was that we had this very nice conjunction where PSP was measuring solar wind flow at a reasonably close distance. Solar orbiter with the METIS instrument was looking perpendicular to that, and so it could in fact see the flow of the solar wind very close into its acceleration region, and Parker Solar Probe could measure, and we showed the same parcel of flow a little while later. And so what we found then was sort of METIS measurements of the electron number density. Gosh, I shouldn't have made those so small, NE, of the radial magnetic field. The speed here showing the acceleration. This was an alphane. I think where was this? This dashed line is the empirical fit, but these are the alphane sort of inferred alphane results, and this was the mass flux over here. And so these are empirical fits, but and here, oops, I'm sorry. And right over here is the flow or the corresponding plasma quantities that were observed by Parker Solar Probe. So what we have with this conjunction is an opportunity to basically look close in and a little while later at the Parker Solar Probe plasma and determine what has happened in between. So these are all empirical fits. We're currently working on doing the modeling to that, but it offers an enormous opportunity for this kind of modeling. And I think the next conjunction is the 2nd of June on 2022. But this first one was quite stunningly interesting. So with that, let me finish and just basically say that we're really living in a golden age for solar and heliospheric physics. And I'm hoping that we're a lot closer to answering the decades-long question of how the solar corona is heated and understanding the origin of the solar wind. So let me stop right there.
Thank you so much, Gary. Thank you so much. It was really fascinating, and I'm sure I'll benefit of the video to look again at the equations we're showing. I don't see question posted during the talk. I maybe can ask one first. So in the one, I think was the third part showing the modeling by Adhikari of the energy deposition into the solar wind. So you were showing this process out from 50 sun radii up to 1 AU. And you said that the most of the energy dissipation happens because the 2D component deposits energy. So, two sides of the question is, so if this is so, we should expect that the energy fraction of the slab to the 2D should be increasing, at least in the interval you were showing, so out of 50 sun radii, right? Mm-hmm. But we see that at least at 1 AU, the fraction is 20%, about 20% for slab and about 80 for the 2D, and seems to be a little bit larger the slab component fraction when you go inside. So it seems that the going outward, the fraction in 2D is going to decrease. So it seems that this is in agreement with what you are saying. Right? But the question was, if you look inside the 50 Saredi, where maybe up to the Earth surface, or even inside, when you go closer and closer to the corona, do you have analysis done? Because we have data also up to 16 sun radii, I think now.
So yeah, that's an interesting question. We've actually have a paper that's submitted, and what the paper shows is that there is a at least within about 0.3 AU, AU into the various perihelia that Parker Solar Probe has made, is that there in fact is a varying ratio of slab to 2D or 2D to slab turbulence, whichever way you want to put it. And so there is variability within that region rather close into the sun. A little further out, it tends to be more or less constant and fixed. So that's sort of what we anticipated. Where the complication arises is that there are, of course, lots of in situ sources of turbulence. So part of the reason that the ratio tends to be maintained in the more distant heliosphere beyond, where Parker Solar, closer to 1 AU and beyond, is that things like stream shear are important as a result of Kelvin-Helmholtz instabilities generating turbulence. And it also appears that as you get quite close to the sun, there is evidence for Kelvin-Helmholtz type instabilities as well. There was a sort of nice couple of papers that Craig DeForest and Bill Matthews and some others did, and I'm sure you're aware of those, showing these large sort of floccules, I think they called them, which seem to be sort of rolled up structures in the solar wind. And as I mentioned way back at the beginning of the presentation, Daniela Taloni and I and several others have looked very closely. Daniela used UVCS observations to try to see if he could extract signatures of a Kelvin-Helmholtz type instability in the subalphanic and slightly superalphanic regime. And we appear to have done that, and there are signatures showing, which we've associated with our modeling, of increased heating there. And so we seem to be seeing evidence, the long and the short of it is, we seem to be seeing evidence of a variable 2D to slab ratio when you get close into the sun. But it is additionally complicated by the presence of turbulent driving, which may be associated with more driving of quasi 2D than slab turbulence.
I see two questions, one from John. John, please.
Hi, Gary.
John,
very
nice.
interesting. One thing that I thought I'd bring up is you mentioned the small magnetic flux ropes.
Mm-hmm.
And a postdoc here, Amy Rivera, has been working on some ionization state anomalies observed with ASAT 1AU, and they're only seen in the slow solar wind and CMEs, but they last for a couple hours, so they're not real big if you extrapolate them back to close to the sun. But basically, the two kind of interesting things, I think, are that because they are ionization state anomalies, they have to arise inside the Friesen height, which is, like 3 solar radii. And the fact is that they do manage to survive all the way out to 1 AU, so they are not dissipated.
So let me ask you a question though. Because you mentioned CMEs, are you seeing these in, say, the body of a CME, or are you seeing them away and from such structures or not?
They are seen sort of in the inside of a CME, but there's no real clear picture. But they are also seen roughly equally in number in just the slow solar wind.
Well, certainly, I would kind of question whether or not you would see them, because as far as I know, and we haven't looked in detail, I have to admit, in terms of ionization and but if I were looking at flux ropes and small scale flux ropes in the inside a CME or some such structure, then I would expect that just from a cascade, because I would expect there to be turbulence, and I would expect there to be a cascading of turbulence in those scales. So if that, if what I'm seeing inside a CME is just small scale flux ropes, I would expect that just based on their dynamical time, stuff has to happen. It just doesn't sit there. Based on their sort of nonlinear and dynamical time scales, that it would more likely be the result of having a cascade process that produced these small scale structures, but done in an environment that is already enriched in certain sort of ionized elements from the initial CME. If I were to look in the vicinity of the heliospheric current sheet and look at small scale structures there, I would be very surprised if I saw evidence of enriched elemental abundances in those, because the heliospheric current sheet, if nothing else, is generally regarded, and I think we've shown that, to be a prolific producer of small scale flux ropes.
Right. Well, these are it's not all flux ropes that show this. It's sort of the other way around, that most of the ionization anomalies are associated with flux ropes, but they do seem to appear quite frequently in the slow solar wind.
Okay, I'll need to think of that's an interesting point. I'd like that. Has that work been submitted, or is it? In fact, I'm trying to think.
You're probably the editor.
Yeah, feeling like,
I don't think it's been submitted yet. I don't remember.
Okay. I saw a paper, although I shouldn't be saying that because Leon's no doubt on the line, but I thought I saw a paper that was not unrelated to that just recently.
Yeah, she does have a related paper or two, but I'm not sure that this one has been submitted yet.
Okay, okay. All right, I'll be very interested in that. That sounds very curious.
Okay, we have another question from Ma Asghari. Ma, please.
Hi, Ma, how are
Hi.
you?
Hi, good, thanks. Thank you for a very interesting talk. I have a question about the quasi 2D turbulence in the low corona. So my first question is, what would be the observational signature of this type of turbulence? And for example, have you considered looking at a spectral line broadening in the observations from instruments such as ICE or others to confirm?
Yeah, that's really difficult. I'm not, unfortunately, familiar enough with that sort of instrumentation to really get a good sense of what could or couldn't be done. There was a paper that I sort of was involved with some years ago with Val Abramenko, where we looked at trying to determine the correlation length lambda perp, which in some ways would be part of the turbulence parcel or the turbulence building block for quasi 2D turbulence. And we were sort of managed to get a sense of what that should be in the photosphere, or just above the photosphere, I guess. And it turned out, I forget the exact number, I use it all, we use it in our models, but it turned out to be quite surprisingly small. Now, I don't know whether a related technique like that would work, because that effectively is a measure, I thought, of quasi 2D turbulence in the low corona. And if I recall correctly, I thought that they tended to find spectrum that looked like basically a k to the minus 5/3 in the perpendicular wave number. But much more than that, I'm kind of afraid to go out too much on the limb.
Sure, thank you. I have one more question, sorry, about the unidirectional turbulence that you said. Don't you still need the outward propagating waves and inward propagating waves to be interacting, to have, even if you have only one wave, if it's the outward, you would still get some kind of reflection back so that you could have the turbulence. Is it the case?
So this is really why it was interesting and such a puzzle. So in both cases, the one example was that Daniel Telloni looked at. We were looking at wind data in that particular case, so roughly at 1 AU, and there we found these highly field-aligned regions. There were, as I said, I think only 17 that we found. In each case, it was unidirectional propagating alphanic fluctuations. There was virtually nothing that we picked up. I mean, the sigma was like 0.9, sigma cross-helicity was absolute value was about 0.9796. I mean, really high. And you had k to the minus 5/3 spectrum, and the two cases that Lingling Zhao identified in PSP were exactly the same. The cross-helicity was, almost 1. And so there was no counter-propagating waves at all. And so the question is, where then and again, it had this k to the minus 5/3 spectrum. So, in the sort of Goldreich, Sridhar, and the standard sort of large plasma beta description says, you basically have to have counter-propagating alphane waves. You set up then, plus VA, minus VA, you look at the resonance relation, and you need a zero frequency mode, and that produces your nonlinear interaction. But that doesn't exist in this particular case. And so, so there is a way, though, that you can have a coupling of these waves, but it's through, in some sense, a passive. I tend to describe it as a passive scalar coupling of alphanic fluctuations to quasi 2D turbulence. And you can go through that kind of analysis, and it turns out that you can then in effect, do your nonlinear couplings via your 2D couplings and produce a k to the minus 5/3 spectrum. So that's one possible way of producing that. Other than that, kind of, I don't know, it's kind of, you know, I don't know whether if you were really, really close to the Alfvén critical point and you had a k to the minus 5/3 spectrum just below it in Alfvénic fluctuations, and then basically you filtered all the backward propagating modes at the Alfvén critical surface and left only the outward propagating modes going out, whether that would still correspond to the k to the minus 5/3 or not, but I don't know. But it's kind of a weird explanation. But other than that, you know, I can't think of another method or another mechanism that would produce that minus 5/3 spectrum. So it's a real challenge. I mean, it's, you know, I think with the Goldreich and Sridhar sort of approach, I don't know how they can possibly explain that without counter-propagating waves. And in the sort of pure and incompressible MHD, which is valid for large plasma beta regimes, you know, you can't, I don't know how you can easily do that either, how you can explain that observation either.
Thank you.
Thanks, Gary. I don't see other question, and let me thank all those who stayed longer. We went a little bit beyond the scheduled time. So, okay, I think we can close now. Thank you very much, Gary. There is a file spreadsheet, Google spreadsheet. If you want to meet with Gary, you can sign up. There are some slots for tomorrow, I think, still available. So please do that. You can also, of course, just email and ask questions via email. And with that, I think we can close for today. Thank you very much, everyone.